floor at my house, and then I'm not getting that, but I know exactly where it is because I left it on the floor.
Right.
She gets all that, but it's going to play in the house, and then I don't know where it goes.
Oh no, she didn't throw your notes in the trash can, I hope. She better not. Oh, it's time. Okay. So let's see. There is a homework assignment due on Friday. If you don't have the homework, it's homework number 10. It's on Blackboard. I also have some copies here for you guys if there's anybody who doesn't have a copy of the homework. And what we're covering is, and by the way, for the high school folks who missed things, I just now posted the lecture from Friday onto Blackboard, and the lecture from Wednesday is also on Blackboard. So if you missed, you can go through that. So we're covering we're on section 16.3, and we're talking about this nice fundamental theorem for line integrals. And and we're talking about vector fields. So if f is a vector field and f can equal the gradient of some function, so recall the gradient is, of course, small f of x, small f of y, and if it's three-dimensional, small f of z. If it equals that, then the line integral of the vector field f dot dr is equal to the line integral of the gradient of the small f dot dr. And the nice thing is that what that evaluates to is you take that little f function, you plug in the endpoint of your curve, and you subtract f evaluated at the beginning point of the curve in a very similar way that you do with, that you're used to with antiderivatives over an interval. Okay. And recall our definition of a conservative vector field here. Capital F is a conservative vector field if it equals the gradient of some function, for some function f. So therefore we can conclude that if it is a conservative vector field and thus equals the gradient of some function delta f, then we can just evaluate that little f function at the end terminal point minus the initial point and get the value of our line integral. Okay, now we have a term here when the line integral only depends on the beginning and ending points of the curve. We then say that the line integral is independent of path. So it doesn't matter how you get from one point to the other, as long as we're talking about a piecewise smooth curve, the line integral is going to have the same value if it only depends on the beginning and end points. So the question was raised in class, so is there a good, nice method for determining if a given vector field, if it is a conservative vector field, because then if it is a conservative vector field, we have a relatively easy way to evaluate the line integral of the vector field. And we ended class last time with the answer to this question that yes, there is a good method to determine this. And the fact is this: given, and here we're just talking about 2 dimensions right now. Say f of xy, this is our vector field, so it's some function of x and y that we'll call p times the I unit vector, plus another function of x and y that we'll call q times the j unit vector. This vector field is a conservative vector field if and only if we have this a relationship. The partial derivative of the p function with respect to y is equal to the partial derivative of the q function with respect to x. All right? So this is something, let me put that up, this is something you guys should remember. And remember, for the last test and for the final, you can use a front and back cheat sheet. So I'm trying to mark things with asterisks here as we go along. That would be, might probably be a good idea for you to include on that sheet. Okay, so we're going to just go through a couple of examples here of determining whether a given vector field is conservative or not. So let's look at the first example, and the question is determine whether f of xy, which is equal to, okay, the function x minus y times the I function plus x minus 2 times the j function, whether this is a conservative vector field or just is conservative. Okay, so the first one is our p function. The second one there is our q function. No, I'm sorry. This one here, it should be a 2, x minus 2, sorry. So therefore our p is x minus y. So, and our q is equal to x minus 2. So what we do is we take p and do the partial derivative of p with respect to y, and we get -1. And then we do the q function, and we do its partial with respect to x, and we get a +1. So since they're not equal to each other, we can conclude this is not a conservative vector field. Okay, pretty fast to do. Okay, let's look at another example then. Here, our vector field, again, it's 2-dimensional, again, God bless you, is defined like this: 3 plus 2xy times the I function plus x squared minus 3y squared times the j vector rather. All right, so therefore p again is 3 plus 2xy. Q is the second one, x squared minus 3y squared. All right, so we do the first one with respect to y, dp dy, and let's see, the 3 goes away, x is constant, so we get 2x as our result. And then we do dq dx, and that whole second term goes to 0 because it's a constant, and we also get 2x. So therefore, it is a conservative field, vector field. It is a conservative vector field. All right. Okay. All right. Now, the thing is, okay, so we know that this field is a conservative vector field, and suppose we're wanting to evaluate its integral along some curve. Okay, so if we know that a field, capital F, is conservative, how do we go about evaluating the line integral along C of f dot dr? And for those of you who might have missed, say, like Wednesday's class, you can look. We went over in that lecture how we define f dot dr. I might be mentioning that again today, so you want to review that. Okay. So the thing is, if it's conservative, all right, then we know that f is equal to some gradient of f, of some f. Some little f, rather, all right? Okay, so the deal is, how do we find this little f function, all right? The question, how do we find the little f function? Right? Because the line integral is going to be equal to this little f function evaluated at the terminal point of the curve minus the little f function at the start point of the curve. So we need to know what that function is if we want to get a value for this integral. The way we do this is we do something called partial integration, which is kind of the reverse of partial derivatives. So I'll put that in quotes. We use partial integration. All right. So we're going to do that with this field that we were given. Let me put down this field again, fxy equaling the one that we found that was conservative, 3 plus 2xy times the I vector plus x squared minus 3y squared times the j vector. All right? Okay. Now, we know it's conservative. We figured that out. We know it's conservative. So therefore, let me use the bracket notation. So, let's see, the first component of this vector field is 3 plus 2xy, comma. The second component is x squared minus 3y squared. So this thing equals gradient of f for some f, right? Well, what is gradient of f? That means the first component of the gradient is f with the small f with respect to x, comma, the second component in this case is the small f with respect to y. All right? So we have these two equations. We have f with respect to x. I just equate the components. Equate the components. So I have little f with respect to x is equal to 3 plus 2xy. And then let me put over here little f with respect to y is equal to x squared minus 3y squared. And we want to find f. Okay, what I do with, say, the first one on the left is I integrate both sides with respect to x. So integrate with respect to x. All right, so what this is going to give me here then is when I integrate, so I'm going to have integral of the derivative of f with respect to x, but I'm integrating it with respect to x. So when I rewrite this for my next step, what am I going to get? What's the integral of the derivative? Don't they cancel each other out? So this is going to be my little f function on the left. I'm taking the derivative with respect to x, and then I'm integrating with respect to x. So our reverse operations, I will end up with my little f function. Okay? Now, so if I'm integrating the left side of this with respect to x, I have to integrate the right side with respect to x. So I take 3 plus 2xy, integrating with respect to x. Now, we've done this kind of thing before when we were doing areas. When we were computing double integrals, right? We would have maybe 2 variables, or maybe even 3 variables, and we would only be integrating with respect to one of them. So that means we treat the other variables as if they were constants. Okay, this shouldn't be a brand new thing for you guys. So therefore, in this case, y is treated like a constant because we're integrating with respect to x. So let's find the antiderivative here. Okay, 3, the antiderivative of 3 with respect to x is going to be 3x. And then 2xy is going to become 2x squared over 2 times y. So that's going to become, when I simplify it, x squared times y. All right? However, since we're integrating with respect to x, it is possible that our little f function has another term which strictly has y's in it. All right? No x's at all. So what I'm going to put here is, instead of putting a general constant like you're used to doing with antiderivatives, I'm going to put a function of the variable that was treated like a constant. So I'm going to say our little f function is 3x plus x squared times y plus, and now I'll just have to give it a name. I could use any letter of the alphabet. I'm going to say plus some g of y. All right? Because notice, if I then went from this direction, from here back to here, and I took the derivative with respect to x, and we're going in the other direction, the 3x would become a 3, the x squared times y would become 2xy, but the gy, since it's all y, would become a 0, all right, because y would be treated like a constant. So we could have some function hanging out there just of y. Now we do a similar type of thing with the other partial derivative that we have. So we have fy is equal to x squared minus 3y squared. On this one, of course, we're going to integrate with respect to y. So we're going to have the integral of fy dy equals the integral of x squared minus 3y squared dy. All right. Now, on the left-hand side, the operations will cancel themselves out again. I have the partial with respect to y. I'm integrating with respect to y. So I'm still going to end up with little f on the left side. Now, on the right side, I'm integrating with respect to y. So x is a constant. All right? Okay. So the first term, x squared, when I do that antiderivative, I'm going to have to tack on a y. That's going to become x squared times y. And then the second term, all I have is the y. That's going to be minus 3y cubed over 3. So that'll be minus y cubed. And then I could have some other function hanging on at the end, but this time that function would only be a function of x, the other variable that's being treated like a constant. Let me give it a name. I'll call it h of x. All right. So what we end up with here, notice on these two equations, this one and this one, both of them are equal to the same thing. F is our function little f of f is equal to this, little f is equal to that. So what I need to do here is kind of match up the components, because I need to figure out what is that g of y function and what is that h of x function. But we can figure that out by matching corresponding terms. Okay, now notice both of these have x squared times y. So x squared times y matches up with both of them. So let me start my little f function out here. So my little f function, first of all, we know it's going to have x squared times y in it. All right. Now let's see what else both of these have. We know that it also has to have a 3x in it. But notice there isn't any 3x over here on the right-hand side, but what there is this little h function that is a function just of x. So that little h function is the same, or has to be the same, as 3x. So let me add on a second term that we have to have here in my little f, 3x. All right, what else have I not accounted for? Minus y to the third over here. But if we look, we don't have a minus y to the third on this other one, but we do have this small g of y function. So this minus y to the third has to be the same as that one. All right? So I now will add on a third term. Oh, I should have put a minus sign, sorry. Minus y to the third. Okay? All right, so we've matched everything up. The only other thing we could now have with our function is just plus a general constant. We can always tag on a general constant with an antiderivative. So let me put plus c. All right. Now you can check that if you do the partial derivative of this little f function with respect to y, you'll come and get this x squared minus 3y squared. If you do the partial derivative with respect to x, you'll come and get 3 plus 2xy. Okay? So this is our little f function that we need. All right. Okay, so let's now let's see here. All right, let's then do, let's get a curve. We need to get a curve. All right, so let's do this. So given capital F, our vector field, equal, it's the same thing. I'm still using the same vector field. 3 plus 2xy times I plus x squared minus 3y squared times j. Now we want to evaluate the line integral of the vector field along a curve C, and we're now given a specific curve where C is equal to r of t, which is equal to e to the t sine of t times the I function, I vector rather, plus e to the t cosine t times the j vector. And t goes from 0 to pi, because we have to have endpoints for it. All right. Okay. Well, we've determined that this is a conservative field. We have figured out what little f is. Little f, so capital F is equal to the gradient of f, where f of xy, let me repeat what it is. It's x squared times y plus 3x minus y to the third plus capital C. So, this vector integral will be easy to do. Here's my curve. I'm basically going to my initial point, let's see, what are my values for my initial point? This is when t is equal to 0. All right, so my initial point is going to be e to the 0 power times the sine of 0, so that's going to be 0. And then my x component is going to be e to the 0 power, which is 1, times cosine of 0, which is also 1. So my x is going to be, my y component is going to be 1. So here's my x and y for my initial point of the curve. And then my terminal point, that occurs when t is equal to pi. So let me plug these into the curve. So when t is equal to pi, I'm still going to have 0 here for the first component. I have e to the pi power, but I have the sine of pi, which is 0. So therefore, my first component is going to be 0 again. Now I plug it into my second component, e to the pi times cosine of pi. So let me write it down here. It'll be e to the pi times cosine of pi. But we know cosine of pi is -1. So my y component of my terminal point is going to be minus e raised to the pi power. Kind of a strange little value, but that's what it is. All I'm doing here is plugging this into my curve. All right? Okay, so let's get here. Let me put a little line. So this value of this line integral then is going to be my little f function that I found. First of all, I'm going to evaluate it at my terminal point. So that's going to be 0, evaluated at 0, comma, minus e to the pi power. And then subtract, and then evaluate it at my initial point, which is 0, comma 1. Okay? So are we all right with that? Even though we have a rather strange coordinate there, I hope we're okay with the process. Finding the x and y of the beginning and the end of the curve by plugging in the parameters. Do you have a question?
Well, in the past, we were getting things in terms of t, and now we're just using t again.
Right. Because our little f function is the function of x and y. Okay? So we have a curve that's parameterized with that single variable t, but it has a first component and a second component. We have to plug the beginning value of t to get the first x and y, okay, for the initial x and y, and the last value of the t to get the terminal point x and y. Okay, all right. Okay, so now let's see, what did we figure out? Oh, here's here's the function we're going to use right here. So I plug in these values into my little f function that I figured out. Now notice here, since x is 0, the first term is going to be 0, the second term is going to be 0. I do have to plug in this. So this is minus y to the third power. So this is a little tricky. It's minus, now my y value is equal to minus e to the pi power. So I have to take that in parentheses and raise it to the third power. And I'm going to do this just for the heck of it. I'm going to tack on that plus c. All right, but it's going to go away. Okay, that's plugging in at the ending point. Then it's minus, and now I plug it in at the beginning point. Again, x is 0, so this first and second term both are zeros. I plug in 1 into my y to the third. So I need to also, again, to use parentheses. That's going to be minus for the minus there, and then 1 to the third is a 1. So I'm going to have a double negative there. And then also, here, I need to actually put brackets here. Since I'm insisting on putting the C in here, I need to, if I'm going to tack on that C. But, yeah, just a second. I think I probably already know what you're going to ask. I don't have to worry about this C at all. I'm just doing it for illustration. What happens here is that the C's cancel out. So what do we have here? We've got a minus raised to the third power. That's going to be a negative. And then we're taking a negative of a negative. So that's going to give us a positive E. And what power will E be raised to? 3 pi. Remember, Jenna, tattoo time. Power to a power, you multiply the exponents. Okay, so 3 pi. All right, and then here, and then we have a plus C, but I'm going to get rid of it in a second. And then we have a double minus for the 1, so that's going to be plus 1. And then we have a minus C. The C's, no matter what their value are, will cancel each other out. And you can, in fact, just say, well, let C equal to 0. Was that your question? You're good? Okay. So this is so this is our answer here. So it's e to the 3 pi power plus 1 is our evaluation. That's our answer. Okay. All right. Now, so in 2 dimensions, we have a test for determining whether a vector field is conservative or not. All right. Now, in section 16.5, which I think we might get to, they tell about a test in 3 dimensions to determine whether a vector field is conservative or not. All right. So if and when we get to 16.5, we'll talk about that then. Okay, so this could be the work done. That's what I'm thinking of. The example that we saw as far as like physics is concerned, we saw that this that work done is could be equal to it's like moving a force along this curve C. The work done is an example of what this thing equals. Because remember, and maybe this is, I'll put this down here for people who missed it, what does this thing mean? It means we're doing the integral along the curve C of our force dot product with our unit tangent vector ds, all right? And we showed that, and we showed that what this is equal to is the integral along the curve C of, let's suppose f is equal to pxy times the I vector plus qxy times the j vector. We showed that this is equal to the first component function p dx plus the second component q dy. All right. And then all right. And so, let's see, what do I want to say with this? And then we know that to figure out, to determine what this is, we have to, if we don't have this nice fact that it is a conservative vector field, okay, we then have to parameterize the curve. We have to parameterize it. So we have from A to B, and then this is going to be P with our parameterization of our curve plugged into it, and then this is going to be what? It'll be x prime of t dt. That's the first component. And then we have the second component, again with the parameterization plugged in, y prime of t dt. All right? this is where C is equal to R of T, where T goes from A to B. And I know that I had told you guys to asterisk this the last time to be able to apply this, because we have to have a parameterization in order to evaluate a line integral. Okay, so I just put like a whole lecture right there on half of a page for you folks who missed it. What I want to show, though, next is this. Okay, in 16.5, if we get to it, we'll see how to determine if a vector field in 3 dimensions, if a vector field in R3 is conservative, okay? But what I want to do now is, let's say that we have determined that a vector field is conservative in 3D. We don't know how we've done it, but we've determined that. Okay, so let's say that capital F of x, y, and z, this is our vector field, it's equal to this, y squared times the I component plus parentheses 2xy plus e to the 3z power times the j component plus 3y e to the 3z times the k component. Okay, suppose we know this is conservative. I'll put somehow. Suppose we know somehow it's conservative. All right. What we're going to do now is find the little f function such that it is the gradient of the little f function. So what we're going to do now is find little f of x, y, and z such that our capital F vector field is equal to the gradient of that function. Because if it's conservative, we know that that is the case. All right. Now, what I'm going to do here is very similar to what we did in the 2-dimension case. First of all, let me rewrite. I'll use the bracket notation, our force field, our vector field. The first component is y squared. The second component is 2xy plus e to the 3z. And the third component is 3y e to the 3z. So that's in brackets. And it's equal to, for some little f, it's equal to fx, comma, fy, comma, fz. We don't know what that little f is. We're going to find out what it is. Okay. So just as before, we equate the components. And we do partial integration. So let's do the first component. We have fx is equal to y squared. All right. So what we want to do is take the partial, integrate both sides with respect to x. So we integrate the fx with respect to x and integrate y squared with respect to x. Well, the left side will give us is going to equal whatever our little f function is. On the right side, when we integrate with respect to x, y and the variable z are constant. Now we only have the variable y here. That antiderivative is going to be y squared times x. But this time, we could have this extra function that's hanging around at the end could also be a function not only of y, but also of z, the other two variables. So I'm going to put plus, I'll call it g of y comma z. Either one of those either or both of those variables. Now let's go on to the second, let's leave that for right now and go on to the second component. Here we have fy and that's equal to 2xy plus e to the 3z. And now this time we integrate both sides with respect to y. So integrate fy with respect to y, and integrate 2xy plus e to the 3z with respect to y. Okay, that means x and z are constant. X and z are constant. Again, on the left side, when we do the integration, we end up with a little f. Okay, x and z are constant, so we have two terms here. The first one is 2xy. Y is our variable, so we do y squared over 2, but then the 2's cancel out. So this first antiderivative is going to be xy squared. And if you're alert, you see that in that first one, we already got an xy squared. All right. Now, there's a second term here, e to the 3z. Z is a constant. E, of course, is a constant. Its antiderivative with respect to y is going to be e to the 3z times y. Now, this time, we could have another function hanging on at the end that's a function strictly of x and z. So I'm going to give it a name, call it h of x and z. And we'll do the comparison after we get all three of them down there. All right, now we go on to the third component, and that's fz is equal to 3y e to the 3z. Okay. We do its antiderivative with respect to z. So integral of fz dz equals integral of 3y e to the 3z with respect to z. All right. So again, that left side is going to just be our f function. And on our integral, y and x are constants. We don't have an x, we do have a y. Z is our only variable, so we're going to do that antiderivative of e to the 3z, and we're going to quickly know how to do that. E to the 3z with respect to z, we know is 1 over 3 e to the 3z. We take the number in front of the variable, we divide by it. So we can get that antiderivative quickly. So then we have a 3 in the denominator, a 3 in the numerator. They will cancel each other out, and our antiderivative then will be y e to the 3z. And then, again, we have this function hanging around of both y and x, and I'll call it, let's see, we have g, we have h, I'll just call it little I of x and y. All right. So we have to do this extra step because we have three components. All right. Now it's a matter of comparing and seeing what we're going to have in our function. Again, all three of these are equal to the same thing, f, f, and f. All right. Okay, notice here not all of them, but the first two have an xy squared. So we're definitely going to have that. So this is now going to be f of x, y, and z. And now the third one doesn't have an xy squared, but it has some function of x and y. Well, that's going to be the xy squared. All right, these all equal each other. So let's start, so our first term, let's write it as xy squared. Now let's look at what else we have here. In the second one, we have this y times e to the 3z, and we have it here for the second one, and we have it again for the third one. Notice we don't have it specifically for the first one, but we have a function g of y and z. So that's going to be the same thing. So that g of yz is going to be the same as that e to the 3z times y, e to the 3z times y. So let's add on here. Let's write it as y e to the 3z. Okay. And let's see. That's it. This function here of x and z, it has no match with the other ones. So that is just going to be a general constant. So we can always tack on a general constant of c. But otherwise, we've matched everything up. So that's our little f function. All right. And basically then, if you need to, you can directly verify, you can directly verify that the gradient of this function is equal to, let's just put our capital F function that we started with. You can verify that, okay? All right, and so if we were going to evaluate this integral that along a curve, we would evaluate our little f function on the end of the curve minus at the beginning of the curve, okay? And I think that just leaves us with a couple more minutes, so that's the last thing I had on this chapter or section, so we'll end it there. Next time on Wednesday, we're going to have Green's theorem. So I was going to put this to a vote of how many think I need to dye my hair green for Wednesday. Jenna's, I'll put myself totally at the mercy of everybody here. And if you vote, yes, I'll do it because it's Green's theorem, and we've got to have green. So anyway, we're going to cover 16.4. We should be able to get through all of that on Wednesday. So anyway, see you guys then.